In this lecture, we introduce limits. Consider a point P and some nearby points Q. We want to know how the function f of x changes at the point P. This is the point down toward the bottom in our picture. But we might, to figure out the slope at the point P, we might compute the average rate of change as the second point Q approaches the first. That is, the distance between the 2 points shrinks to 0. The instantaneous rate of change is the slope of the function at the point P. We approximate it by the average rate of change, but the slope of the lines between the points P and say Q1 in red, or P and the line through Q2 also in red. Notice that the points Q1, Q2, and Q3 all approach P so that the red slopes, the red lines, approach the tangent line in purple. We're going to approximate the instantaneous rate of change by the average rate of change. The IRC is the limit of the average rate of change. The average rate of change is a slope. It's the change in y values on top in the numerator divided by the change in x values, here it's h, in the denominator. As the points Q get closer to P, this denominator h gets close to 0, goes to 0. The instantaneous rate of change has an inherent difficulty. It takes the idea of the ARC, the slope of a secant line between 2 points, and attempts to identify a tangent line hitting the curve at a single point. We don't know how to create a line through a single point. We do know how to create lines through 2 points. A single point does not define a line. We don't let that bother us though, because we're guided to this purple tangent line by the red secant lines. But to be precise about the IRC, we need to first develop the idea of a limit. The concept of limit, like the limit of a sequence, the limit of a function, the limit of a sequence of functions, is a fundamental idea in calculus, in modern mathematics and the sciences. We will look at a function f of x near some x value, x equals a, and we'll ask about the limit of the function of the y values at the value a. We say that this limit is the y value, y equals L, if we can force the y values coming out of f of x to be arbitrarily close to L by choosing x values close to a. Our notation is this. This expression says the limit as x approaches a of f of x equals L. And it means that we can force the y values close to capital L by forcing the x values close to a. For example, suppose f of x is x squared. The notation limit of x squared as x approaches 3 equals 9 means that we can force the quantities x squared arbitrarily close to 9 by picking x values close to 3. For example, if we want x squared within 0.1 of 9, say between 8.9 and 9.1, we can do that by plugging in numbers like 2.99 or 3.01 or 2.995. If you take any of those numbers and you square them, you'll get very close to 9 within 0.1. This is an important concept I want to stress in this slide. The concept of limit at a very deliberately has nothing to do or nothing to say about the value of the function at x equals a. We do not care about what happens at a. We want to know what happens nearby. We do not care whether f of a is defined or what its value is. We're only concerned about what happens near x equals a. For example, consider this function. This function is undefined at x equals 3 since the denominator is 0 there. We cannot plug in 3 into this function. But if x is close to 3, like 2.99, not equal to 3 but close, then f of x can be simplified. Since x is close to 3 but not equal to 3, then the denominator x minus 3 is not 0, and we can simplify this to x squared. And so f of 2.99 is just 2.99 squared, and in general, x values close to 3 will lead to function outputs close to 9. So the limit, as x approaches 3, of this quantity is 9. From time to time, we require that x approach the x value a from a particular direction. We might insist that x approach along the x-axis from the left, from below a, and write the limit as x approaches a from below of f of x. The minus sign as a superscript above a means that we're using x values to the left of a on the x-axis, numbers a little bit smaller than a. We could instead insist that x approach a from the right along the x-axis from values larger than a. When we do this, we write the limit as x approaches a from above. Here the x values are slightly larger than a, and so on the x-axis they're just to the right of a. If we do not choose a side, coming at a from the left or the right, if there's no superscript, then we're allowing the x values to approach a from either direction, and so we will leave off a superscript and just write the limit as x approaches a. This should be the same as the limit from the below or the left and limits from above or the right. We'll look at limits in three ways: geometrically, using a graph, via tables, using a calculator, algebraically using manipulations and substitution. We begin in the next presentation with the geometric understanding of limits.